Hello everybody, and welcome to the final video in this small series on propensity score methods. I'm Jan, and this video will show you an empirical example of the methods we spoke about in the 3 previous videos. To get details, I highly recommend you to check out the previous videos, but obviously if you are familiar with the issues, you can also just watch this video. First, I will show you the 2 different processes that we use as examples. Then, using my generated data from these processes, we'll compare the different methods we spoke about. And finally, I will show you an example of the property of balance of the propensity score. For this video, I generated some data myself. We are interested in the income returns to going to college based on a number of different variables. I repeated each analysis 10,000 times so that the results that we get are not just due to chance. You can see the whole distribution. In each analysis, we say we have cross-sectional data from 750 people. I have prepared 2 different processes. You can pause the video to look at the data in more detail. I'll briefly cover the most important details. The first process is the simple process. We have 2 independent variables beside going to college, namely IQ and an ambition score. The process that generates the income is relatively linear, although we have a minor interaction term between ambition and income, IQ here. The equation to determine selection into college is also relatively linear and determined by a logit model. Note that here, IQ and ambition determine both the selection and the outcome. The complicated process has more variables. Beside IQ and ambition, I also include talent, a dummy for being black, and a dummy for being female. Black and female are generated completely independently from the other variables, while talent is correlated with both IQ and ambition. In our equation to determine income, we now have a couple more interaction terms. For example, this one, this one, this one. I've also included a wage penalty for blacks and females, reflecting the pay gaps that we see in everyday life. Importantly, the returns to college are now heterogeneous. Here we interact college with talent, for example. More intelligent people and more talented people have higher returns of going to college. The selection process is somewhat more linear. Women are more likely to attend college, while black people are slightly less likely. Now, before we dive into the model comparison of using different estimators, let's now take a brief look at the data. Here is an example of data generated using the simple process. For the income process, you can clearly see that people who go to college earn more than people who don't go to college. If you compare the numbers though, you see that they're not close to the 500, which is the actual return to treatment if you look back at the slides. That means that simply comparing means we underestimate the returns to college. The picture for the complicated process looks quite similar. Now let's look at the propensity scores. The simple process, which I put on the left, has lots of overlap. If you remember, that will be great for our assumption of common support. Naturally, those who go to college have a higher probability than those who don't, but the difference here is not too large. Now, when we look at the complicated process on the right, the picture isn't as nice. There's lots of observations at the corners and not all that much overlap. We'll have to keep that in mind when we look at the methods now. Alright, let's look at the meat of this video, the comparison of the different methods. Let's look at the most important comparison first, that between a very broad range of different methods. On the left is the graphs for the simple process, on the right the ones for the complicated process. I show you here the histograms for the deviations from the true treatment effect that I found when I ran my simulations those 10,000 times. Ideally, we'd want the histogram to center around 0, so that there are no systematic deviations, and to cluster around 0 quite tightly. Now, the top graphs show us the results for the naive estimator for the average causal effect, that is, the simple comparison of means. In both cases, we see that the returns to college are always overestimated, because the talented and intelligent people are both more likely to go to college and will themselves earn more. Definitely not great performance, as you'd expect. If you want to hear more about this performance, you can check out my video on the fundamental problem. The second estimator, in the second row, is for regression adjustment. The simple process is quite close to linear, so simple linear regression actually does pretty well. The distribution even looks very close to a normal distribution, at least from our bird's view that we have. For the complicated process, linear regression is definitely closer to the true treatment effect than the naive estimator, but it still underestimates it quite substantially. Next up is inverse probability weighting. I've applied the tricks we spoke about in the previous videos. I'll show you the effects of these tricks directly in a bit. We see that inverse probability weighting is quite similar to the effect of regression adjustment. The variance is slightly larger. That's mainly because inverse probability weighting uses fewer observations because of clipping. For the complicated process though, inverse probability weighting actually does a better job than regression adjustment. Because of its high variance, there are a few observations that are even more of than regression adjustment, but the distribution as a whole has much more mass to the right of regression adjustment. You can remember the process for the propensity score was less complicated than the process for the outcome. Finally, in the last row, we have a matching estimator. Here, this one is based on covariate matching. The matching estimator is also not centered on 0, but here, interestingly, has a positive bias in both cases. When you view these results, you should bear in mind that I have included the variables that determine selection and outcome. That is, I have all the variables that are necessary for the selection on observables assumption, although I might not have specified the process correctly. In the real world, this might not be the case. There might be selection on unobservables going on, and then any of these methods will fail. Now, let's dive deeper into the different models that are based on the propensity score. First, we look at the tricks for inverse probability weighting that I mentioned previously. The first row shows us estimates using the raw propensity score. Those estimates are all over the place, pretty horrible. The second row shows us trimmed estimates, that is, clipped to those with propensity scores between 0.1 and 0.9. Those are better, but for practical purposes, still not great. The last row not only clips the observations, but also normalizes them. That actually looks pretty good. I found this fascinating because I wouldn't have expected that effect is so enormous. Like, just compare the second row and the third row. So the takeaway is you should definitely clip and normalize your data. Now let's look at different ways to use the propensity score. In the top row, we have our old inverse probability weighting. Alternatively, in the second row, we can use the propensity score as a regressor in linear regression. The nice thing here is that you don't have to clip, so you can retain all your observations. That means that the distribution is typically a bit tighter, as you can see here, than an inverse probability weighting. The third row uses the inverse propensity score as weights in a regression. The last row shows us results with propensity score matching. It doesn't look that great with much higher variance. That's often a problem with matching estimators, since you sometimes have to throw away a good number of observations without a good match. If you remember the previous histogram of the propensity scores. But there's also an alternative explanation. I'm not all that familiar with matching estimators yet, so it might also just be that I messed up an option in the program. As a final comparison, let's look at how the double robust estimator performs. In the top row, we have regression adjustment. In the second row, we have the inverse probability weighting. For the simple process, we already said that regression adjustment performs a bit better, while for the complicated process, the inverse probability estimator is probably better. Now, what's interesting, when we look at the double robust estimator for the simple process, we see that it is pretty close to the regression adjustment estimator, so the one that we thought was better. For the complicated process, the double robust estimator is definitely better than the regression adjustment. Its mass is shifted towards 0, which is what we want. 0 deviations from the true average treatment effect. It might even be better than inverse probability weighting. The distribution looks like they have approximately the same centers, but the double robust estimator is tighter, so it's less likely to get really off value for the returns to college. The last thing we'll look at is the property of balance. In the second video of this series, we've proven that once we know the propensity score, the covariates hold no more information on treatment status. That means that, conditional on the propensity score, the covariates are mean independent of treatment status. That's something that we've used, for example, when we use the propensity score in the regression. Now, this property too is something you can test. A very simple way is by stratification, so let's look at that. In this table, we have the mean values of covariates by treatment status. I've only used the simple process here, so we have fewer variables to consider. As you can see, people who went to college are both more intelligent and have higher ambition. That's not surprising, since I generated the data to look exactly like this. We can also again see that the comparison of average earnings is pretty misleading. Remember that the actual average treatment effect is not even heterogeneous and lies at 500. This is clearly larger than 500 by quite a margin. Now, what happens if we stratify based on the propensity score? In this table, I stratified into 4 different areas of the propensity score. This upper left table gives us the mean values for those with a propensity score between 0 and 0.25. Here, this one gives us those with a propensity score between 0.25 and 0.5. Here, between 0.5 and 0.75. And here, between 0.75 and 1. Now, in the first table and the fourth table, we still see quite a large difference in means for the covariates, although you can check that they are slightly smaller than the difference we've had here. Pause the video if you want to verify this. Now that's because of a failure of the common support assumption. You can skip back in the video to see the histogram of the propensity scores for this process. So here you can see quite well that this assumption matters practically. Now let's focus on the 2 middle tables. Here the difference in the means are definitely much smaller than when we didn't stratify. Here, for IQ, the difference was previously 12 points, and now it's less than 1. It's 0.1 difference in IQ, 0.2 difference in IQ score. Much smaller. If we had found substantial differences within these strata, the common support assumption would seem violated. So we probably didn't model the propensity score correctly. What are the consequences? Well, it could be that you didn't model the propensity score correctly, and a few interaction terms already can help you with that. Alternatively, it could be more severe and your selection on observables assumption doesn't hold. There's an unobserved variable causing everything to go amiss. Another interesting feature in this table, by the way, is that the two middle tables actually give pretty good estimates of the treatment effect if we compare the means of income between college and non-college students. So that's a final estimator that you can use to calculate the average treatment effect. Alright, lots of things we spoke about today. So, what are the key takeaways? Firstly, you should always check the common support assumption, for example by plotting the propensity score by treatment status and checking the property of balance. That you can do, for example, by stratification, stratifying the covariates based on the propensity score. Secondly, different estimators work differently in different contexts. Sometimes regression adjustment works better. Sometimes estimators based on the propensity score work better. Double robust estimators, at least sometimes, provide a nice middle ground, but you should generally think about which process is simpler to model. Thirdly, if you do any weighting with propensity scores, you should clip the data and normalize the weights, or disaster ensues. I hope you enjoyed this video and the series. If you did, please leave a like and subscribe to the channel to keep up to date with new videos. If you have any questions, feel free to leave them in the comments and I'll do my best to answer them. Thank you.